Dualities and Deformations, and welcome to Humboldt University in Berlin. I'm happy to see so many of you here, so many familiar faces and so many new faces. So I hope you're all looking as forward to the talks as I am. But before we get started, I just want to briefly acknowledge the German Science Foundation, the DFG, the Foundation La Caixa, and the IGFAE in Santiago de Compostela for their financial support in organizing this event. Then some practical announcements. I'll try to keep this very brief. Please make sure that you all register and pick up your badge. This is important for our administration and, for example, for the conference dinner. If you have urgent questions or issues, please talk to one of the organizers or the conference secretary or one of my PhD students or something like this during the breaks. We all have these blue lanyards. Yeah. So for local issues, it's of course better to talk to the local people. For general conference-related issues, you can talk to any of us. Right, so in terms of Corona, please all wear a mask if you can, and please do a self-test if you haven't done one. And in case you have symptoms, you can get both masks and tests for free at the registration desk. Then in terms of internet, if you have Eduroam, everything should work fine. If you do not have internet, Eduroam and you need to use the internet, please talk to me or Rob over here. Right, then coffee breaks, lunch, and reception today will all take place outside here in the hall and outside here in front of the building. So there's seating outside as well. There should always be vegan and vegetarian options available. But during the coffee breaks, the vegan options beyond the fruit are kind of limited, so please don't take this unless you actually registered as being vegan. Right, then I'll say more practical things at the end of the day today, but now it's time for the first talk. So for this is my pleasure to introduce Arkady Zeitlin from Imperial College London, who will tell us about reproducing gauge theory free energies from the string side of ADS-CFT and how this can be quite subtle. So please go ahead, Arkady.
Thank you much. Yeah. Yes, I think so. Yeah. Okay. Let me start with thanking the organizers. So it's a pleasure to be here in Berlin again, and I'll start with somewhat mixed topic talk, which is a little bit out of the main theme of the conference, but at the same time it's kind of quite close and maybe will give some different perspective on some things. So what I'm going to talk about is based on several papers. And my talk will be, if I'll manage on time, will be having two parts. One will be about some n equal 2 models and their free energy as it follows from localization. And then the second part will be based on this last paper, most recent paper. Well, actually, there are two recent papers, but this one, the last one, which is about how we can understand this free energy from supergravity, at least the leading term in the free energy. So let me start from far away, and just to mention that we're coming close to 25th anniversary of ADS-CFT. And what we know so far, on one hand, is quite a lot, on the other hand, is limited. And what we understand more or less is how the duality works in the planar limit, and that is based on integrability. But if we go beyond planar limit, we face the questions of what happens with 1 over n corrections, and there are some other observables which one may also ask whether they are controlled by integrability. So just to set up the notation, this is a very familiar story. So for exact correspondence, we need to keep G string and string tension arbitrary, or the same as saying the J Young Mills and N of SUN group. But then we can consider Toft limit in which we expand at large n at fixed lambda, and then we can expand in large lambda, and that's the most obvious comparison which goes in when we look at strings, weak coupled strings, and try to take large lambda expansion on gauge side. So working out large lambda expansion direct on gauge side is a challenge, but for some particular observables that's possible, and that will be related to what I'm going to talk about. So again, starting from some general comments, so why we're interested in the integrability. So on one hand, if we have integrability, we can say something about string spectrum in curved backgrounds, particular special curved backgrounds. At least we hope that integrability allows us to find the spectrum of energies, and EDS spaces provide examples. On gauge side, integrability is present in at one loop order in all sorts of gauge theories, but beyond that, in N=4 theory, we have integrability at the leading order in large n expansion. So integrability controls a spectrum of anomalous dimensions and possibly some correlators. So it applies for any value of the parameters. So large n, but any value of gauge coupling. So what about finite n? And later on we'll also ask about less supersymmetric theories. So here we may hope that there are also other methods may be useful. In particular, localization applies in supersymmetric case, which could be n=2, possibly n=1, but it only applies to certain special observables. So it's kind of limited in scope, but it applies for any n and any lambda. And then there is also bootstrap, which is based on quite general principles, but it's not particularly useful to getting some explicit information apart from some bounds, and in some cases, the very sharp restriction on region of parameters. So there was some recent progress on combining these different methods, maybe combining even integrability and localization and bootstrap to gain some information about some particular correlators and trying to understand what would be the interpretation ADS as some scattering amplitudes in ADS, etc. So if you go back to IGST conference, you will see, for example, talk by Aldai discussing some of this. So if we try to go beyond n=4, so one simplest possible case is to consider certain orbifolds or antifolds of n=4 theory. And indeed, there are special n=2 superconformal theories which are planar equivalent to n=4. And these are the simplest examples to study. So they will be controlled by at least their untwisted sector will be controlled by integrability. They are planar equivalent to n=4. They will be integrable in that limit, just equivalent to n=4. But then one could ask what happens in twisted sector, or what happens when we go beyond the planar limit. What happens including 1/n corrections. And that will be the main topic of what I'm going to talk about. So in n=2 models, localization matrix model, so here localization applies, and it applies to particular observable, which I'll be discussing, which is free energy, which is essentially logarithm of partition function of a gauge theory defined on for sphere. So one could also discuss, there are closely related observables like BPS Wilson loop and also correlators of some chiral primaries, but I will focus only on free energy. So this free energy can be computed using localization matrix model. And it will be depending on n and gauge coupling. And then we can consider expansion at large lambda and try to see whether we can compare to string theory. So that's essentially the circle of ideas which I want to address. So the challenge would be really, there are two challenges. How to expand the result of localization matrix model at large lambda. This is a technical challenge, as will be clear later. but also technical and conceptual challenges how to compute this on string side, this free energy, and to compare to localization result. Just to give some perspective on what I'm going to talk about, let's start with the simplest example, namely free energy in N=4 theory. So we consider N=4 theory defined on 4 sphere. And N=4 theory is finite, but if you define it in curved space, in general, there are ultraviolet divergence, which is controlled by conformal anomaly. So in the case of 4 sphere, this is just a coefficient of conformal anomaly proportional to dimension of the group. So the free energy is just this divergence. R is the radius over the 4 sphere, UV divergence plus some constant. And this constant clearly depends on the scheme because there is ultraviolet divergence. Depending how you subtract it, you can change this constant. So if you consider, so this is just from quantum field theory perspective, and that free energy doesn't depend on 't Hooft coupling a priori because A is just, it's not randomized. The constant may depend on lambda depending how we decide to define this object. Now, on localization side, we're dealing with Gaussian matrix model, in this case of N=4 theory, and assuming particular measure, which essentially is like a special scheme, and dropping divergence as it's done when defined in localization matrix model, one gets the following result. So essentially, one gets the same coefficient A, which is the dimension of the group, times logarithm of 't Hooft coupling, lambda, plus a constant which is just function of n, which is related to dimension of SUN group. So that's the result which comes from localization matrix model. So this log lambda is may look strange, but it's some power of lambda in the partition function. So what would be the analog of that from on dual side? So from ADS CFT side, free energy should be matched to string partition function, first quantized string partition function on ADS 5S5, which should be properly defined in the tree level, namely large n. That's two-sphere topology in string theory. This is essentially like supergravity action. There will be no alpha prime corrections in this case. This is just ADS 5S5. It has maximal supersymmetric vacuum. So essentially supergravity action, you look at supergravity action and you conclude that it's proportional to the volume of ADS 5. This step is not completely innocent, as I'll discuss in the second part of my talk. So why supergravity action is just a volume of ADS 5 on ADS 5S5 space. But let's assume that's the case. Then this volume is infrared divergent. If you introduce cutoff on the radial direction of ADS, you get log divergence proportional to the coefficient A, which is the same conformal anomaly coefficient, which is just proportional to n squared at leading order at supergravity level. And then if we decide to fix this infrared cutoff in ADS in a very special way, as was suggested by these authors, then one can match precisely this log lambda. So just picking up this infrared cutoff in such a way that it gives us just lambda, we get matching with this localization matrix model result. So this is a little bit ad hoc, and indeed why we should pick this particular cutoff, but there is some logic that this is natural in the case of ADS CFT if we want to match these expressions. As for -1, it comes from one loop effect, which is torus topology on the string side. So indeed, one can argue that computing one loop string correction, which in this case just boils down to one loop supergravity, one reproduces also this -1 in this expression, this one. So that's essentially how comparison should go, and one would like to generalize it to say N=2 models. So what do we know about these N=2 models? There are, in fact, very special, there are very few simplest superconformal models which are planar equivalent to N=4. And so that means they have simple ADS dual. And to find them is basically one needs to look at one loop beta function of gauge theory. So in N=2 case, beta function is just given by one loop coefficient. So if you take a SUN group, the simplest choice of representations is just some number of hypermultiplets in the joint, fundamental rank 2 symmetric, rank 2 antisymmetric. So these are lowest dimension representations. If you go to high dimension representation, you'll never manage to match beta function. So there are very few particular theories, and I'll call one of them contains symmetric plus antisymmetric representations. So rank 2 symmetric, rank 2 antisymmetric hypermultiplets, and another contains some number of fundamentals and antisymmetric. So I'll call them SA theory and FA theory. So SA has one symmetric, one antisymmetric, no fundamental multiplets. FA has 4 fundamentals and 2 antisymmetric. So these SA and FA models are essentially may be viewed as orbifold and identifold projections of N=4 theory, and they will be due to similar projections of AdS5S5. So again, to emphasize demanding conformal invariance and planar equivalence to N=4 selects very special theories for the simplest group SUN. And just to give an idea why they are planar equivalent, you can look at conformal anomalies of these theories, and they all start with n equals n squared. So in FA theory, which has fundamentals, there is also the difference comes in at order n. So n squared terms match with N=4 theory, but already at order n there is a difference in conformal anomalies. But conformal anomaly is just controlled by free theory, essentially. There's no interactions involved. Now, another very special theory is found when you take a group, when we take a group SP to N. So here, conformal invariance condition, again, one loop beta function, selects particular theory, which is a FA model, again, fundamentals plus antisymmetric, but here we have 4 fundamentals and 1 antisymmetric to match the beta function. And similarly, this is the conformal anomaly again N=4. So N=4 has dimension, or adjoint is n times 2n plus 1. I mean, the group SP to n has these dimensions. So it's essentially that's what appears in the A anomaly. But in N=2 theory, the second coefficient is different compared to that one. So what about localization matrix models? So in these N=2 models, we can apply localization. And just to recall what this localization is about, essentially we define N=2 model in a 4th sphere. This has to do with regularizing infrared divergences. And the way how this is done was done by Pistun. It's a kind of special way of defining both the measure and the integrand. So that corresponds to a particular scheme in this language of which I mentioned earlier. So what localization is about? The claim is that path integral of gauge theory is reduced to integral over one constant scalar mode. There are 6 scalars in, well, there are not 6 scalars. There are N=2 vector multiplet in the case of N=2 coupled to hypermultiplet. So in N=2 vector multiplet, there are scalars. So you could pick up one scalar. So this scalar, or in N=4 language, that will be the scale of one of the 6 scalars of N=4. So this scalar has an action which comes just from very special terms in the N=4 theory defined on the 4th sphere. In particular, there is a term where you have a scalar coupled to R6, so this conformal coupling of a scalar on curved space. So for sphere, curvature is non-zero. So you get, from this term, you get trace A squared term. So A is a constant mode of this scalar phi. So it's essentially, in SUN case, adjoint matrix. Sorry, not adjoint, Hermitian matrix A. So the expression which is written here, there is some measure of integrating over A. The free action comes from that term, essentially, plus some other term, but it's basically proportional to gauge coupling, 1 over G Young-Mills, or lambda over n, times this trace A squared. And there is a one loop term, or interacting part of this action of matrix model, which I'll describe on next slide, but in N=4 theory, there is no this term. So that's essentially the measure, the action. So if you do the integration, it's like Gaussian matrix model. It just gives us this coefficient in power how many matrices you have. So it's essentially dimension of the group. And with some normalization to on the volume of the gauge group, that gives this prefactor C. So that's how this formula comes out of localization matrix model. So free energy is just logarithm of Z is just logarithm of lambda times dimension of the group. Now, in the n equal 2 models, with some number of hypers and some representations, if we consider Lagrange expansion, we can ignore instantons. And then the expression for this integrand in the matrix model is just a ratio of determinants, one-loop determinants. So you just take n equal 2 or n equal 4 model, you expand it in this constant A background, and consider one-loop fluctuations. And these are these determinants. I'm not going to explain in detail, but it's essentially determinants of Laplacians with mass terms, which determined by this constant A, on a four sphere. So it's an infinite product over modes, and you need to regularize it. That's essentially what gives this log divergence in general, but if you regularize it in a certain way, you end up with this particular expression for this one loop term, which determines the interaction part of the action. Of the action of the matrix model. So what appears here is a product of two, what's called Barnes function. It's essentially a function which satisfies this relation with gamma function. So if you shift the argument by 1, you get multiplication by gamma. It's an infinite product of some sort. I will show you more explicitly. But essentially, the one-loop term in the matrix model, determining interaction part of the action, is given by some special function, which is a kind of infinite product. So that's what one should take of this. So in these n equal 2 models, explicitly we can just write everything in terms of eigenvalues of the matrix A. So that will be a path integral like this with a particular measure, one Demont determinant, etc. But what is important, so this is what's important where Yang-Mills coupling is, so lambda over n. It only comes here in in S0, as interaction term doesn't depend on gauge coupling. It's just these one loop determinants, they depend only on A. And this interaction part, that's how it looks like. So this H matrix, it's essentially this infinite product. So here it's redefined a little bit. So depending on number of multiplets, the interaction part contains various terms of log H with different arguments. Again, AR are eigenvalues of this matrix A. So this H is this product, and a logarithm of H has a very simple form. Well, simple sum. So log of H of this function is just powers of X, the argument, with coefficient, which is values of the Riemann zeta function times this prefactor. So what one needs to do, one needs to pick up particular model, and then sum up these interaction terms, and that will be infinite number of terms. So it's kind of complicated interaction term. And that's explicitly how they look like for particular models. So for SA model, which has equal number of symmetric and symmetric, after redefining A like this by lambda, so that kinetic term is just Gaussian without any coupling, the coupling appears in the interaction term now as lambda in some powers. And in this SA model, we just get double trace interactions. And that means this H depends on both the eigenvalues. And these are coefficients which appear. Again, some values of zeta functions, gamma factorials, etc. So that's very explicit, but quite complicated. So the moral of this is that if you want to develop perturbation theory in lambda, this is straightforward. Just powers of lambda appearing in interaction terms. You can do integral over A to any given order in A. In lambda, you just expand in lambda. But what if you want to know large lambda expansion? And that's a challenge, because somehow we need to understand how to do large lambda expansion here. For any finite n. So n, I'm not touching n so far. I'm just assuming we will be also expanding in 1 over n, because we dropped instantons. So what we want to compute is free energy. And the first leading term in free energy will be, again, Yang-Mills term, planar equivalent theory. So this interaction will go away at least this order. But if we take a difference between this, say, free energy of this SA model and Young-Mills, that will be 1 over n squared correction, leading 1 over n squared correction. And that's what we'll be interested in. So we normalize essentially to that super Young-Mills, and would like to find how this delta F will look like at large lambda. So similar story explicitly for FA model with fundamentals and 2 antisymmetric. So here the interaction term contains extra term, so similar double trace term as before, as in the previous theory, but there's also single trace term. With coefficient, again, there's some zeta function. So here, because of this single trace term, or because of the fundamentals present, there is the delta F, the difference with super Young-Mills, starts with order n term. So previously it was just order n squared term, or order n in power 1. So the leading term goes as n squared, Young-Mills goes as n squared, subleading term goes as just with n in power 0. So here, in addition, there is term of order n. So if we finally go to SP model, this is actually the simplest model for which one can get quite explicit expressions. So it turns out this SP to n model with 4 fundamentals, 1 antisymmetric is the simplest model. In this case, interaction term has just single trace interactions. And here one could work out quite explicitly what are these terms in 1 over n expansion in free energy for any lambda. So the leading term F1 is essentially an integral of Bessel's with lambda entering like this as argument of J1. So you can do this integral that way or another and work out what's lambda, large lambda expansion. So again, small lambda expansion is straightforward, but large lambda needs some work, and that's what we get if we do this. We get term of order lambda, log lambda, some constant. A is some glacier constant, but what's important, then there's 1 over lambda term and then nothing. And then there are exponential corrections. So they just follow from this integral. And all terms like F2, F3, etc., they're all determined by this F1 through derivatives or integrals. So they're all related to F1. That's a claim that follows from this structure of this matrix model. So essentially knowing this and taking derivatives and integrals, etc., you can work out the whole series. So what happens to be exact result is has the following structure. So the free energy is just n squared plus n. So n squared is again will be n equal 4 theory with group S2Pn, and n squared plus n plus constant log lambda. I'll explain what lambda prime in a second. Then constant, then term 1 over lambda, and then exponential corrections. So lambda prime here is redefined lambda. It corresponds to shifting Young-Mills coupling by a constant, log 2. It happens that it looks like a scheme change, but indeed this is kind of encoded in the structure of this matrix model that there is this shift. And this shift resums all sorts of terms with log 2, which appears as subleading one. So in principle, that's an explicit expression. So we'd like to match this to string theory. So that's essentially the main aim. So let me quickly say what is known about other models. So again, SP2N model is the simplest, but in other models can also say something about at least leading 1 over n squared correction to free energy. So structurally, the simplest is orbifold model, which essentially is just quiver with equal couplings. So SUN with two adjoint, two B fundamental multiplets, which connect these two groups. So this is just essentially can be thought of as an orbifold of n equal 2, n equal 4 theory. It's planar equivalent to n equal 4. It's dual to orbifold on the string side. And what is important for me here is that we can work out the strong coupling expansion of the free energy in this case using particular form of this correction to free energy, which follows from matrix model. So matrix model, one can show that delta F, then namely the 1 over n squared correction to free energy, is determined by logarithm of determinant of semi-infinite matrix. Just particular matrix, which is integral of product of two Bessels, like this. There are two of them, m plus, m minus. So obviously these are integrals which you can expand in small lambda, and then you get the result in a series of lambda. But at large lambda you can also expand them, but that's not legitimate because we're supposed to do infinite product, infinite determinant first. So it's actually non-trivial how to work out the strong coupling expansion. Interestingly, the precisely similar, well, quite similar expressions like log determinant of some semi-infinite matrix appears in a different context, what's called octagon correlator in NeCo4 theory. It's a particular correlator of large R charge 4 BPS operators with large R charge scaled to infinity. So in this case, it was understood how to work out this correlator for particular values of x. Well, I'm not going to discuss details. All I want to say is that similar object appears there. And using this technique, we recently understood how to find strong coupling expansion also for this case. And what one finds is that this orbifold theory, free energy goes like this. So again, it contains log lambda, but it also has square root of lambda as a first term, then there's some constant, and then series of terms 1 over lambda. Here, lambda prime is different. It's redefinition of lambda itself by log 2. So the series here, which is written here, there is I here. So that indicates this is just particular way to defining this infinite sum. The sum is not convergent, not Borel summable, and here these non-perturbative corrections are kind of imaginary. These are all details. I'm not going to discuss non-perturbative corrections. What is important is that the structure of this series is, in all these cases, is consistent with what you would expect from string side, namely expansion alpha prime 1 over square root of lambda. So this, again, to summarize, the free energy expanded at large n is having this kind of series expansion. Why square root of lambda? We will need to understand why it starts like that. There's no good reason, but a similar structure is precisely for this octagon, where the square root of lambda was, so again, octagon is like partition function, it's exponent of f. So there is a square root of lambda in exponent, and then that suggests some semi-classical string interpretation. It will not apply here. It has nothing to do with minimal surface, etc. But interestingly, it has similar structure. Just to say that in this other model, I say similar story applies. Again, the planar correction has log determinant expression, and essentially a similar series is found also here. So this orbifold theory, SUN, SUN, and SA model is very similar. FA model is kind of a cross between SP2N model with fundamentals and this SA model. It has also order n term, and then there are other terms which contain similar corrections. And here, F1 is essentially the same as SP2N model. So these are all details. Let me quickly say something about dual string interpretation. So for orbifold theory, I already mentioned this is just orbifold of ADS5S5. This is old story. Particular Z2 orbifold. And in principle, one could ask what will get computing string partition function in this case. For SA model, there is an orientifold involved as well. And there's a particular way to define which orientifold we should take to get the dual theory. The logic here is you need to kind of first start with flat space, geometrically engineer this theory, and then translate this to the ADS5S5. So there is some orbifolding involved. There is a Welchit parity and the fermion number projection. So again, I'm not going to go into details. This is not, we actually didn't apply that so far, this knowledge. But one could make it quite explicit what kind of identification of angles one needs in S5 to define this projection. For fundamentals, this geometric engineering involves putting n D3 branes, some number of D7 branes, And to balance D7 brane, one needs also O7 plane. So there is orientifolding involved as well. And again, there is a particular orientifold which corresponds to this SUN FA theory. And similarly, again, there is essentially it's ADS5 S5 with some particular projection of S5. Similarly for SP2N with fundamentals here, this theory was actually discussed early on, back in '98. It was understood how to reproduce conformal anomaly, at least a conformal anomaly, in the using this intuition that you should have D3 branes plus D7 brane plus O7 plane, or that's particular projection of ADS5 S5. So once we have fundamentals, there is open string sector, so that means the corrections goes as 1 over n in power odd number. And again, I don't have time to go into details, but it's important to keep in mind that once we have these orientifolds, we also have cross-cup contributions. Not plus, once we have orientifold plane, we have cross-cups. Once we have fundamentals, that means there is D7 brane on which open strings can end. There's also boundaries. So you need to consider both sheets, not only sphere with handles, but sphere with cross-cups, sphere with holes. So if we want to compute free energy, we essentially want to compute string partition function on ADS5 with this on ADS5 with project S5, including all these topologies. So depending on theory, you want to look at particular topology. So let's start with simplest guess that say the free energy should be given just by effective action of some sort of type 2B theory with all sorts of corrections. So at free energy, at tree level, it should be just R4 type correction, and then there are one loop corrections. Say in orbifold theory, there will be R4 one loop. And one could ask whether this can give us what we actually get from localization matrix model. So I already discussed that story, so the story which in n equal 4, but let's look at, say, orbifold theory. So the result in orbifold theory, again, starts with leading correction is lambda 1/2. So that coefficient can be understood from projection, the volume, counting the volume, shifting n. But the interest is this lambda 1/2. And here we don't have a good idea apart from the fact that if you just look at R4 term, there is, in type 2B theory, there is R4 correction, 1 over alpha prime. And just on dimensional grounds, if you imagine evaluating this on ADS5 S5, that will give us precisely the scale, which is L squared over alpha prime, and that gives lambda 1/2. So it looks like one loop term should give us free energy, which scales as lambda 1/2. But the puzzle is that this one loop R4 term is exactly the same as tree level R4. And tree level R4 evaluated on ADS5 S5 should be absent because we don't have any correction at order n squared, at leading order. So it doesn't seem to be the right explanation. And furthermore, if we evaluate R4 on ADS5 S5, the S5 is projected, but ADS5 is unchanged. So R4 will just give us volume of ADS5 back. So from the volume of space, you just get volume of ADS5. It's still extended in ADS5. And that will give us, by that logic of cutoff, logarithm from the volume of ADS5. But there's no log in front of this square root of lambda. So it's not clear how to get this lambda 1/2. So it most likely comes from torus contribution, not effective action. One should not use this intuition that partition function is given by effective action. Anyway, I don't have much time to say anything about FA theory. So again, there's more a question how we're going to understand matching to string theory. Important point is that here we need to keep track of this or the n corrections, and indeed there is a way to understand this log lambda correction coming for the n from the effective action point of view. It's essentially similar to what happens for conformal anomaly. How much time I have?
You're good. 20 minutes.
Okay, very good. So just to take a few remarks to take of this out of this discussion is that once we are dealing with theories with fundamentals, there should be order n terms. And that intuitively interpretation is that there is a D3 brane, large number of D3 branes and small number of D7 branes originally. But that's kind of intuition from flat space, but in ADS5S5, you're just dealing with some particular projection of the theory. So that's order n terms. And exponential corrections, in principle, may have interpretation of world-sheet instantons. A reason for that is that once we have some projection of S5, there could be wrappings on S2 which are non-contractible due to orbifolding. So in principle, that could be interpretation of these non-perturbative exponential corrections. The exponential corrections are the ones which I mentioned when I discussed this SP2N theory. They just come from the expansion of this Bessel. You naturally get terms like this without any I. In this case, this is order n term. This series is barrel summable. It's just this integral. So so that's different from this 1/n squared corrections. Unfortunately, everything is mixed up here. So just to summarize this part of what I just talked about. So some comments and open questions. So there is a lot of interesting data about strong coupling expansion. It comes from localization. And it looks kind of organized the way so that it should match to string theory. It is quite surprising. If you just look at the starting points, it's not clear why it should have this particular 1/√lambda expansion. So, and we are not talking about planar limit now. We are talking about 1/n and 1/n squared corrections. So they are subleading. So it's definitely required to have better understanding of this analytic control. It's only very recently that it was understood how to work out these large lambda expansions, which I discussed. What remains to be done a lot of open questions is on string side, how to do simplest loop computation on string side beyond planar limit, beyond tree level. So now, what about the role of integrability? It plays no role at all in the discussion which I gave about localization. So localization matrix model is more or less just supersymmetry. But it may have some hidden role. A reason for that is, well, one circumstantial evidence is that there are very similar structures, these Bessel candles, appear in planar super-Young-Mills. I mentioned this octagon correlated. And in 1/n squared corrections in these n=2 models. So why that happens, we don't know, but these should be related to integrability, sort of, because this octagon construction was based on hexagon construction, which is sort of based on integrability. Now, the deeper reason could be that integrability actually controls the spectrum of strings. And when we compute loops, we glue this spectrum in, we use this spectrum to construct loops. So once we have correlators, it's less obvious, but say for free energy, it's just vacuum loops, so maybe integrability actually controls them in some way. So that's a very interesting question, but so far there is no good evidence. There is also twisted sector of orbifolding, which already is non-trivial at linear order n squared. And that raises the question whether these n=2 models are actually integrable, including twisted sector, already at planar limit. And maybe we'll hear something. Well, there was a talk by Eli Pomoni at Integrability conference, and that I'm not sure that's related to that, but at least morally it's related to the question of integrability of n=2 models. So there's a very interesting question whether one could combine somehow integrability and localization. Then there is also a question of about less supersymmetric orbifolds, and again, maybe integrability may have some consequences here. So now I switch to a different topic. Well, it's the same topic, but much more elementary, and which I kind of glossed over when I discussed the free energy of n=4. Namely, what's the value of type 2b supergravity action on ADS5S5? So usually, if you look at papers that discuss application of ADS-CFT for this particular ADS5S5 case, everything starts with this action in 5 dimensions. So we assume we compactify in S5, and we just write down 5-dimensional gravity plus cosmological constants. So essentially gauge supergravity, n equal for 8 gauge supergravity action in 5 dimensions. So then if you pick up the ADS5 vacuum, you get volume. This action becomes a volume of ADS5. Now, if you introduce S4 as a boundary of ADS5, regularized as we just discussed, you get this n squared. The volume with the cutoff, infrared cutoff, it just goes like this. So just to recall, the kappa 5 is related to volume of S5 and kappa 10, and the kappa 10 is related to string coupling, and the radius of ADS is related to string coupling. What did I do here? I think I have too much here. Yeah, either n or G string. Anyway, there is yeah, these are volumes of. Important point is the volume of ADS5 is goes as logarithm. So what, in fact, we get if we just start from 10-dimensional action? So if you look at 10-dimensional supergravity action, that's how it looks like. Very familiar. So F5 is self-dual, but we don't impose this at the level of the action. Normally, we impose this condition on equation of motion. But what if we just take that action and evaluate it on ADS5? Clearly, we just get 0. F5 squared is 0, scalar is 0, and the action is trivially 0. So the bulk supergravity action on ADS5 S5 is 0. So there's a paradox. How could it be that this action is 0 on ADS5 S5, which is a vacuum, but 5-dimensional action is not? And it's a 5-dimensional action which is actually consistent with ADS-CFT. All sorts of applications to, say, black holes, etc., are all based on this action. And in some sense, it's kind of obvious that the two actions need not agree, you may think, because when we use some particular ansatz, like compactifying S5, substitute in the action, and then it's not the same as going through equations of motion and reconstructing action for reduced number of variables. But the values of action on the full solutions, on the vacuum solutions, is actually still expected to match. And moreover, it's 10-dimensional action, which is fundamental. We should follow from string theory. So if you want to know about alpha prime correction, we should start with 10-dimensional approach. We can't just go to 5 dimensions straightforwardly, unless we have systematic way to do that, but not through equation of motion. So one may think that this paradox is related to self-duality of F5, and in fact, it's not quite right. The reason is that you can also consider, say, ADS3S3 with their three-form flux is self-dual, but there's no condition of self-duality on the three-form in the action. So it's not a question about writing action for self-dual field, it's rather property of a solution. So there, also the action will vanish, 10-dimensional, 6-dimensional action will vanish, but 3-dimensional action will be not vanishing. So anyway, so the point of this story is that something is missing. And there's a particular boundary term which is missing, and it's not a Gibbons-Hawking-York term, and also not the terms which needed to make 5-dimensional action finite on solutions with AES5 asymptotic. It's something else, and in general, the general point is that one may, depending on which space vacuum one considers, one may need to add particular boundary topological terms to the bulk action. Flat space is one thing, ADS5 is another thing, and they may have different boundary terms which are relevant. For example, Gibbons-Hawking-York term is vanishing on ADS, but important for asymptotic flat conditions. So what we're going to do is to discuss that particular example when we have a topology of M5 times X5, where M5 is non-compact, X5 is compact. And that covers all sorts of solutions like ADS5, S5, D3 branes, and all that. So just to emphasize again, string effective action has a particular origin from, it's related to string partition function. And the fact that it vanishes on solutions has fundamental meaning. It's related to conformal invariance. So if you look at bosonic string and look at the bulk action of the bulk action is proportional to conformal anomaly. So Lagrangian, written like this, is proportional to conformal anomaly. So it vanishes once you have conformal invariance. So this conformal anomaly is written like this. So there is a dilaton boundary term which one needs to keep in mind considering asymptotically flat conditions. But bulk term is vanishing. And in type 2b theory, an SNS part is the same, will be treated the same way like in bosonic case. Ramon terms need more attention. So in particular, there will be, on equation of motion, there will be boundary terms coming, say, from F3 squared term. F5 is still squared, is 0 on shell, so here we definitely need something else to get non-zero value of the action. And what we need is a term like this. So we can't have F5 topological term, which is trivially 0 if you just interchange the numbers of fields, you get minus sign, and so it should be 0, but if you have topology like M5X5, for that particular topology, you can write a term like this. So you take essentially like electric and magnetic parts of F5 and take a product of them. And that boils down to compactifying on X5, that boils down to integral of F5 over 5-dimensional space, which is essentially cosmological constant. It's just a volume form of the 5-dimensional space, or that's equivalent form. So the suggestion is that we need to add this term with some particular coefficient a priori for that particular topology. So it could appear. And it doesn't change equation of motion. It's a total derivative, sort of, but you need to have such term a priori. So what is interesting, well, you need to fix particular coefficient gamma if you want to match this 5-dimensional reduced action. So this coefficient in front should be very special. And what this special coefficient is doing, actually, it's very simple. It's essentially reverses the sign of electric and magnetic parts in F5 squared. So on the usual self-dual solution, F5 squared is just 0. But if you reverse the sign, it will be non-zero, and that will be surviving. And remarkably, precisely that term with that particular coefficient also comes out of Pasti-Sorokin-Tanin formulation of 10-dimensional supergravity action. And there was a similar recent, somewhat similar reformulation of F5 self-duality of an action for type 2b supergravity where self-duality is not imposed by hand but follows from equation of motion. It also leads to similar term. The bottom line is that I don't need to know about this self-duality problem, et cetera, et cetera. We just can argue that just on general grounds, we may add extra topological terms in particular topological case. So that's the logic. How that follows from string theory, that's an open question. And here at the moment, we're just at the level of supergravity. So in general, the bulk, the total action for particular asymptotic boundary conditions, this M5X5, it will have this topological term plus Gibbons-Hawking term a priori, the boundary term, and the total action will be the bulk plus topological plus boundary. So I just mentioned that this topological term essentially reduces to the volume form in 5 dimensions after we compactify on X5, which is, in the case of ADS5, S5 is just volume of 5 sphere. So we end up with precisely total action being just given by topological term, which is the volume of ADS5. So that generalizes to any X5, which could be any Einstein manifold. And that matches the prediction of ADS-CFT about the conformal anomaly coefficient. So usually we take some ADS 5 times X5 and ask what's the conformal anomaly in this case, and that produces this prefactor K, which is the ratio of volumes. And that will come out of this, this term as well. To further elaborate on this relation of this topological term and 5-dimensional reduced action, which I started with, again, that was my first slide of this part, was just this 5-dimensional action, which is reduced action with cosmological constant. So suppose we want to compare these actions more generally, namely 10-dimensional action for M5 times, say, S5 general ansatz and this 5-dimensional action. So we take 10-dimensional metric like 5-dimensional metric, some scalar nu, which is the kind of prefect of S5, And it's balanced so that there's no new prefactor in the R term. And the 5 form can be kind of general with the condition that these are just volumes of the corresponding 5 space and S5. A in general is this coefficient is in general is a function still. And so this is kind of off shell. So what you'll get if you just compactify on S5 using these ansatz? You'll get R5 plus this scalar nu plus some potential. And that's how this potential will look like. So if you use equation of motion for the scalar A, these two terms cancel, and we do not get the right cosmological term constant in the reduced theory. So that's the counterpart of the statement that if you start with 10-dimensional action, F5 squared is 0, so you don't getting the right action for the reduced theory if you just do naive reduction. But instead, if you use a 10-dimensional equation of motion and reconstruct 5-dimensional effective action, you get this potential instead of this. 3 terms, you get 2 terms, and here I fixed B already 1, which is fixed by equation of motion. So what this potential is saying is that it has a minimum, and at the minimum, minimum is here is nu just nu equals 0. At the minimum, you get cosmological constant, precisely the one which is required in this reduced action. So this V tilde is the potential which comes out if you add this topological term. So if you start with bulk 10-dimensional action, add topological term, you get precisely this V tilde potential. And that matches, this kind of extends this 5-dimensional reduced action with just cosmological constant to the case when there are extra scalar nu, which is a excited radius of S5. So similar story can be repeated for other solutions, like D3 brane solution, full D3 brane solution with asymptotically flat region included in the harmonic function. So that's the expression. It has still M5, X5 topology, so it's easy to see why. Now, so near the core, of course, we go back to ADS5, S5, but here the bulk action again for this solution is still 0. F5 squared is 0. And the scalar curvature is also 0. There's no dilaton here, so this is easy to see. But if you compute topological term, you just get precisely same as it happens that the Gibbons-Hawking-York term gives, yeah, I'm finishing soon, gives what it gives. It gives the integral of the along the volume of the worldsheet volume of D3 brane. That's these y coordinates. 4 y coordinates are the direction along the 3 brane. So just evaluating topological term gives the tension of 3 brane, or this prefactor, times this volume. And same comes from boundary term in this case, where we have a asymptotically flat region. And total action is just this. So that is to say that the topological term contributes the same value as the Gibbons-Hawking term in this case. So the total action is just some number of D3 branes, tension of D3 brane, and world volume. And one can also add the source term, which produces this delta function with HR, and it also contributes the same. So the lesson is that the topological term is as relevant as any other term. And you need to keep it in mind, otherwise you get wrong total value of the action because the bulk term vanishes. So same can be repeated for non-extremal D3 brane, which is relevant for black hole thermodynamics, and also for composite solutions like smeared BPS intersection of D3 branes. In particular, we can consider intersection of 2 D3 branes, which near the core is the ADS3 S3T4. So it's kind of generalized ADS3 S3T4. Or 4 D3 branes, which generalizes ADS2 S2 times T6. So I just flash this here. So for example, for 2 D3 brane intersections, that's how it looks like. And again, you have it no longer has naive, this, you may say it still has M5, X5 topology, but here is not really, what is really relevant is that F5 doesn't have this decomposition. Instead, it has still electric plus magnetic decomposition. Electric means part with time direction, and magnetic is the complement to it. And the topological term still has the same form. So just you take electric part of C4, compute F5 electric, and compute this topological term. And it gives a result which is consistent with naive reduction, well, not naive reduction, but through equation of motion, reduction to 3 dimensions, where you get the value, which is just volume of EDS3. Same story for 4D3 brane intersection. It's kind of look more messy, but again, there is electric potential, the electric field, magnetic is dual to it, and same story works out. So the same for EDS2 is 2. So to conclude, so the message of this discussion is that depending on topology or asymptotic boundary conditions, different boundary terms can be relevant. And we knew that, say, for Gibbons-Hawking York term, it's relevant for asymptotically flat, but it's not relevant for ADS boundary conditions. So similarly, there should be topological term if you want to have equivalence of the value of the action obtained through different routes, through equation of motion or from the bulk perspective. And that topological term has this structure. Now, what should I add? Similar terms can be added for other topologies. For example, for M3X3, you need to add this similar term for 3 forms. And M2X2 T6 similar term could be interpreted in terms of electric field in 4 dimensions, electric magnetic field in 4 dimensions, maximum theory. So we don't know what's the string origin of any boundary terms, in fact, and in particular this term. So that's an open question. Whether it can receive alpha prime corrections, it's unlikely, but still also open question. And how we are going to apply this logic to higher order terms, which I discussed in the first part of my talk, is another question. One final remark is that there is quite an interesting story about finite temperature contributions to free energy of n equals 4 theory, free energy at finite temperature. It's not the free energy which I discussed on S4, but rather on the circle times R3 or circle times some compact space. So here, alpha prime corrections are relevant, and they, in fact, by computer science, like R4 correction is relevant. But the value of the action, again, will depend on, possibly depend on this boundary term. So that's also another open question. So I guess I stop here. Thank you very much.
Thank you very much, Arkady, for the nice talk. Any questions? Right, Ellie has a question, maybe. Khalil, can you?
Maybe no, the last 2 points that you just made, the finite temperature and the higher order correction. Can you say a little bit more about that?
No, here I was referring to our old paper with the Gapser and Klibanov about the following thing. You take D3 brane non-extremal, or ne-extremal, and you compute the action, and what do you get at leading order? You get free energy, or you can define entropy just from the value of the action, just like Gibbons and Hawking did. And you get a result that free energy scales n squared times power of whatever, T4 times the volume. Then there are corrections to that formula, which come from alpha prime, and they come from R4. And the leading correction goes as zeta 3 over lambda in power 3 halves, and that's alpha prime cube. So that value was obtained, and even the first leading term was obtained by starting with 5-dimensional action. What I'm saying is that this needs to be rethought if you want to start with 10-dimensional action. So the result is correct, but the way how this should follow from 10 dimensions, that...
If I want to think that I want to compute the Wilson loop, I want to compute corrections at finite temperature.
Wilson loop?
Yeah.
Why Wilson loop? Oh, Wilson loop is a different story, yeah. I had in mind just simplest free energy or entropy.
But is it clear to you what would be the leading, would that be the leading...
Leading to Wilson loop? You
Yes,
want to consider what?
If I have the 10-dimensional perspective now.
If I have 10-dimensional perspective, and why Wilson loop? Because of S1, because of temperature, why?
Just because it's an S observable.
Yeah, well, yeah, that will be a different story. Yeah, but regarding Wilson loops, in the previous story, there is a story about Wilson loops for n equal 2, but I guess you're not asking about that. You're asking about
I mean both.
both. Yeah, okay. So for n equal 2 models, well, first for n equal 4 theory, there is a Wilson loop observable. So free energy looks kind of trivial, well, simple, like log lambda for n equal 4 theory. But Wilson loop story is more interesting in the way that, as was found by Gross and Drucker, it's given by circular Wilson loop is given by some Laguerre polynomial as function of n and lambda. So it's more complicated than a non-trivial formula. And for n equal 2 models, the leading 1 over n squared correction for Wilson loop is actually determined by free energy. It's some derivative of free energy. So once we know free energy, we actually can compute also correction to Wilson loop. But in principle, this is also an interesting question, how we reproduce that on string side. Because reproducing Wilson loop and free energy is completely different. It's kind of phrased differently on string side. You look at minimal surfaces, the corrections to minimal surfaces, while here we look at just some closed string partition function. So in principle, it's kind of, the question is very relevant. And from string side, these are two very different observables. From localization, they're kind of related because they can compute it in a similar way.
Any further questions? All right.
Thanks. I didn't completely, I lost the ADS3 S3 story. So you say that for ADS3 S3, you need to add on the F3 F3
yeah,
term?
you may ask what about H3? Yeah, you may also worry about H3.
But
H3.
also earlier on, you were talking about the deep brain action that leads to ADS3 S3, and it seemed to there you seem to
What?
this one here.
Yes.
And there you seem to not need the F3 term.
Yes, because, well, if you look at your latest paper, you know that this background can be supported by different fluxes.
So you say, oh.
So
Yeah.
this particular case is the case
With
where
no-
you have just F5. So this particular space can be supported just by combination of F5. It comes out of this limit, yeah. Is it the right slide? Yeah, that's the right slide. Yeah, so if you just take that background and consider near horizon limit, drop this one, you will get geometry which is ADS3 S3 times T4, but the flux is just F5 flux.
So you say that you would generate the new boundary terms by S-duality or something?
Yes,
Right.
yes. So in principle, this boundary term should be related.
So if
by
you impose
duality.
S-duality invariance on the boundary terms, can
S-duality,
you...
well, S-duality just maps this to itself.
No, I mean, if you take your
If you-
boundary term
i-
F5 for F5 and demand...
Here you will need to generate the other fluxes. You will need to do whatever T-dualities as well.
T-duality, okay.
U-dualities, yes. T-dualities, yeah.
Okay.
Any further questions? If not, I have a quick question. So is there some sort of first principle that fixes these topological terms that you have to add that you could have known before realizing there was a paradox that you should have added them? Or
Well, I mentioned this in principle. You can change perspective completely and start with some whatever democratic formulation of fluxes and plus formulation where self-duality doesn't is not imposed at the level of the action, and ask what you actually get there. And this in PST formulation turns out that if you demand under some assumptions gauge invariance, you need to write the action in such a way that this term is there automatically. And moreover, in this other formulation, looks like there's a way to write this as if you don't know which background you're considering. It just turns out that in that background it will be non-zero, on the other background it will be zero. So that kind of logic. So yes, a priori I would say it's an open question. It's somewhat, well, logic may be different in different cases. Like in Gibbons-Hawking, you look at derivatives and it's a different perspective. But here it looks like it's a different principle which you are requiring.
Okay. Okay.
Yeah, I think this is the best I can answer. At the moment.
Okay. Thank you. Okay. Let's quickly thank Arkady once again. So please feel free to talk to him again during the coffee break, which is now. It's right out here. Please be back here by 12 for the talk. Next talk. Yes. Thank you.
Hello. Hi.
Hello, everyone. Hello, everyone. Welcome to the second talk. Before we start, just a few administrative notes. If you need an attendance certificate, please talk to Jenny or send her an email. For the coffee breaks, please put your cups, plates, and so on in the sort of, I don't know, boxes that are provided for it. And it would be great if at the end of the week you can like leave your lanyards here at the registration desk or something like this. Yes? Thank you very much. So then it's time for our second talk. So I have the pleasure of introducing Sibyl Drizen, who will tell us something that covers, or that fits quite nicely with the theme of the conference. So something about integrability and dualities, and this applied in the context of string sigma models. So please go ahead.
Thank you. So first, of course, let me thank the organizers for giving me the opportunity to present this work and the organization of this nice conference. I'm sure the rest of the week will be great. So I will talk about work that I did in the last 1.5 years or so, which consists of two main topics, two research lines that I did together. Both of them I did together with Ricardo Borsato, who is also here. And then a number of collaborators, including Falk Hassler, who is also here, Luis Miramontes, and Juan Miguel Nieto, who should also be here, and then Leander Ruiz. So the two lines or topics that I will be discussing, so the first one consists of the question to understand when we have a supergravity solution, if we could generate new 10-dimensional supergravity solutions. And there's several transformations now that are able to do that. And so we want to understand how, if there is more options, if there is some room to wiggle. And as I will show you in the talk, we will do that by reformulating the problem in some efficient way. And interestingly, this way of reformulating it tells you that at the same time, these transformations will also be canonical transformations at the level of the world sheet that gives rise to this supergravity background. And this brings me to the second topic, namely, if you would have an integrable sigma model, if you have a transformation that is a canonical transformation on the world sheet, then you would also generate a new integrable sigma model. And we will use the fact that we have a canonical transformation to treat this undeformed model and this deformed model at the same footing, as I will show you. Now, the broad motivation to have in mind is that generating supergravities or generating integrable sigma models gives you some sort of organizing principle for these theories, so in the landscape of string vacua, if you want, or in the landscape of integrable theories. Now, we know very well that if we deform such models, that in general we get some very complicated backgrounds, also some complicated world sheet theories. But because we preserve integrability, we still have a high level of analytical control in principle. So at the same time, also there's, this is because of course we know several integrable methods to solve your theory. And so looking at this generation of new integrable models allows you to perhaps generalize also these integral methods to these more general cases. Now, more directly, from the point of view of holography, we are of course interested in this because these transformations that preserve supergravity and integrability are very interesting to possibly generalize ADS-CFT, namely possibly breaking some supersymmetry and maybe some conformal symmetries while you're still having this analytical control of integrability. Okay, so as a proof of concept of these two topics, so generating supergravities and integrable models, I will focus in this talk on the homogeneous Yang-Baxter deformations. So they have these two properties. And they're also interesting because they capture the very well-known TST transformations, and they generalize this to a non-abelian setting, as I will explain. So in the talk, I will show you why these homogeneous Yang-Baxter deformations are supergravity solution generating techniques, how you can very efficiently see that they are supergravity solution generating techniques, and using this reformulation to classify similar transformations that have this property. Then, as I said, they will at the same time be canonical transformations at the level of the world sheet, and I will use that to treat the deformed model and the undeformed model at the same footing at the expense of generalizing your boundary conditions of the world sheet. So I will explain that further. And this in particular has been very useful for us to apply the method of the classical spectral curve and its semi-classical quantization. And this we applied in work that appeared today at the archive to obtain the semi-classical spectrum of a particular Jordanian deformation of the ADS5 cross S5 superstring. And I want to stress that this is a first principle computation without any conjectures based on symmetries. Okay, so before I do that, let me review these very interesting TST transformations and tell you why they are so interesting. So what are their attractive features? So we imagine that we start with some world sheet sigma model that I give here. And we imagine that it corresponds to some integrable sigma model that gives rise to a 10-dimensional supergravity solution. And in addition, we assume that the background has two abelian isometries, so one in x1 and one in x2. So it's hard to point at this thing. Okay, so if you have these abelian isometries, then you can apply a TST transformation. And so what this is just a usual T, an abelian T duality along one of the abelian coordinates, a shift in the other coordinates, and then a T-duality transformation back to your original coordinates. Now, if this model is also a supergravity, then this means performing this transformation, you will generate a new supergravity background, as is very well known, because this just involves abelian T-duality and some coordinate redefinitions, and this is, of course, a symmetry of string theory. So you generate a new metric and a new B field that depend on this deformation parameter, eta, where eta is involved in the shifting of these coordinates. Sorry if I'm not able to point very well, so I hope it will be clear enough. Now, as I said, this is very well known, but it's very nice to see this in the language of double field theory. And for the rest of this talk, the only thing that you should know about double field theory is that it is simply a reformulation of supergravity with some manifest global ODD symmetry. In particular, you go to some doubled space where you have this doubled sort of symmetry, this ODD, where D is a number of the original space-time dimensions. And your field content is then packaged into some doubled objects. So in particular, the metric and the B field of usual supergravity, the G and the B here, they're packaged into this doubled matrix, which is called the generalized metric. And they are packaged in this very particular way. Now, if you perform a TST transformation, you know how the metric and the B field changes, so you can construct this new generalized metric, and you see that what happens is just that you're simply transforming the original generalized metric covariantly with this object S, where S is this matrix of upper triangular form, and beta is some anti-symmetric matrix which depend on this deformation parameter eta. And so that is an element of ODD, and it's a constant element of ODD. And we call this a beta shift, a global beta shift. So you can think of TSTs as just global beta shifts. And because, of course, as I said, double field theory has this manifest global ODD symmetry. If you start from a solution that satisfies the supergravity equations of motion and therefore the double field theory equations of motion, and you apply this transformation, the generalized metric is just transforming covariantly, and then after this transformation, you will still, because it's a symmetry, you'll still solve the supergravity equations of motion. But what is very important is that it's not a trivial transfer. It's not a trivial symmetry transformation at the level of the supergravity background fields. So the generalized metric is transforming covariantly, but it is scrambling the notion of the metric and the B field inside because it's transforming with this upper triangular matrix. So if you read off the new matrix G prime from this object, you will see that it's some scrambling of the original metric and original B field. So to conclude, we already have here supergravity solution generating techniques, and they're captured by non-trivial global ODD elements. So an example is these TST beta shifts, and another example is of course abelian T-duality, where this transformation matrix S is of this off-diagonal form. Okay, so that is the first interesting feature of a TST transformation. The second is that, of course, performing T-duality shifts and T-dualities at the level of the world sheets, they are just canonical transformations and they preserve integrability. Also, this is very well known, but it's very nice to see this at the level of the currents. So I told you to perform a TST, you need these abelian isometries in x1 and x2. And it turns out that, so you can associate to that some abelian Noether currents for the original model and for the form model. And it turns out that on shell, they equate to each other, they coincide with each other. So they satisfy some particular relations in terms of the coordinates, in terms of derivatives of the original coordinates and derivatives of the new coordinates. And these abelian Noether currents, they coincide. And this, so I didn't write it down, but it applies particular relations of this form where we have the spatial derivative to the world sheet space coordinate sigma of the new coordinate x prime minus the spatial derivative to the coordinate sigma, world sheet coordinate sigma of x1, and that should be equal to the Noether current, the time component of the Noether current of the second abelian isometry, and the same happens for these other coordinates. And so this implies that if you integrate this relation and you assume that your new backgrounds just satisfy periodic world sheet boundary conditions, then you will have, for the original background x1, you will have twisted world sheet boundary conditions. And in particular, so we integrate this, we have this periodicity constraint for the new background, but for the original background, the world sheet boundary conditions, this is not zero, but it's given by the integral of the Noether currents, which is just a Noether charge, okay? So, and then we get this very nice picture here, where you can think either in the deformed picture, where the metric is deformed, so you get this sphere, which is a bit squashed. The metric depends on the deformation parameter, but the world sheet, the string, if you go around the spatial coordinate, you just come back to the same value. And this is on-shell equivalent to an undeformed model where the space-time does not depend on the deformation parameter, so it's just some sphere here. But at the level of the world sheet, the non-trivial information about the deformation is captured by this twist. So if you go around the world sheet, you will not end up at the same point, but there is some twist, which I denote by these stars. So as you see, this is already known since 2005, so it's a very nice story that is well understood. So just to summarize, these are the main features that I want you to remember. Of course, to generate a new supergravity solution, we just need to assume that this guy is a supergravity. It doesn't need to be integrable. And then to preserve integrability, we only need to assume that this is integrable. And then, of course, you can have the same things at the same time. Okay, so please interrupt me also for questions if there are any. So now I will generalize this. I will show how these nice features generalize to the homogeneous Yang-Baxter deformations. Okay, So the homogeneous Yang-Baxter deformations, I will show them here for the PCM, for the principal chiral model for simplicity. The principal chiral model is obtained when you send the deformation parameter eta to 0, and then you recognize just a normal action of the PCM where the metric is just some nice group manifold. So here we parameterize this in terms of group elements G, and you obtain the normal sigma model of this form when you introduce some parameterization in these group elements in terms of coordinates. And so turning on the deformation parameter gives you that you stick this particular operator inside, and so that will deform the metric and the B fields. So you get some new expressions that depend on eta. So I told you what is a deformation parameter, but I didn't tell you yet what is this object R, which is called a R operator. Which is acting at the level of the Lie algebra of this Lie group. So it's scrambling the generators of the Lie algebra in some particular way. And it satisfies two important conditions, which we will see coming up during the rest of the talk. So, and they are really the defining properties of a homogeneous Yang-Baxter deformation. The first one is that it satisfies a classical Yang-Baxter equation, which is of this form, and that the guy R is antisymmetric. Now, this is a non-abelian generalization of the TST transformation because this R operator can act non-trivially on a non-abelian algebra G. So the Lie algebra G can be non-abelian. You reduce back to the case of TST when the algebra where the operator is acting on is abelian. So you get we call it an abelian R matrix. And this is just related to the fact that you would have some abelian isometries on which this guy is acting. Okay, good. So now, as I said, the metric and the B field transforms, of course, and the transformation rules are again very nicely captured in the language of double field theory. So again, what happens is that the generalized metric transforms covariantly with some object S. Again, this object S is of upper triangular form. Where beta is an antisymmetric matrix, so it's an element of ODD. But now beta here depends on the coordinates, so it's not a constant. It's not a constant object anymore. And in particular, we see here that we have these, so it's constructed out of the killing vectors of the background, which are associated to the non-abelian isometries. So of course, if you have a non-abelian isometry, the associated killing vector depends on coordinates. If you have an abelian isometry, the killing vector is just constant, and then you reduce back to the TST case. So then this beta becomes this guy here. So homogeneous Yang-Baxter deformations can be seen as local beta shifts. Now you can ask me, well, you told me that double field theory has global ODD symmetry. It doesn't have local ODD symmetry. So why would I still preserve the fact that you have a supergravity? And the reason is that the double field theory equations of motions, they have other symmetries, as I will show. So these other symmetries, they are most conveniently seen in the language of the flux formulation of double field theory. This is just a reformulation in terms of Vielbein. So you go to some Vielbein formalism for the generalized metric H, where E is this generalized Vielbein. And in this formulation, you can construct two interesting objects, which are called the generalized fluxes. They are this particular combination of the generalized Vielbein. So once you have the Vielbein, you can just compute the fluxes straightforwardly. And then you have also this other flux, which only has one index, constructed from the Vielbein, and also an object D, which is called the generalized dilaton. And it's just a combination of the usual dilaton of supergravity and the metric G. Now, in the flux formulation of double field theory, the key point is that the action of double field theory, as well as the equations of motion, can be completely written in terms of these two fluxes, so the flux FABC and the flux FA, as well as their derivatives. So if you would have a transformation that is transforming your background non-trivially, so here in the flux formulation, it's transforming the Vielbein covariantly with this object S. So at the level of the generalized metric, is transforming this in the same way as before. So the background gets deformed, but if you find that your original vielbein gives rise to a flux FABC, and the new vielbein gives rise to a flux F prime ABC, which coincides with the original flux, as well as for these other guys, then you would still solve the solutions of the double field theory when your original model is solving those equations of motion. But as I said, you are scrambling metric and B fields, so you are transforming the background non-trivially. And so this particular transformation happens for homogeneous Yang-Baxter deformations if this operator R satisfies these two defining properties. So if it satisfies the classical Yang-Baxter equation, and if it's antisymmetric, then the flux with three indices will remain invariant. If also the flux with one index remains invariant and you assume that you just go to normal supergravity with a normal dilaton and so on, then you find that the R operator also has to satisfy this condition, which is called the unimodularity condition. It's just some contraction of the R matrix with the structure constants of the Lie algebra. Okay. Good. So what we then did in one part of our work was to look at these transformations and try to classify them and see if there are some more general transformations that, that satisfy these conditions. And of course, as you know, if you want to do a classification, you have to make some assumptions. So we did the same. So we assumed a generalized Schwarz ansatz, which is just a fancy name for us to say that you can decompose your manifold into some external part and some internal part. And the solution generating technique is only acting non-trivially on this internal manifold. In addition, you assume that on this, so the fluxes will decompose in this external part and this internal part, and you assume that the fluxes on the internal manifold are just constant. And in that case, you get a lot of power. So what happens is that identically, you will see that this flux with three indices just satisfies a Jacobi identity. And therefore, you can associate some Lie algebra to it. So I will not go into the detail because I want to cover many topics. But the main point is that you have some doubled Lie algebra which you can use to really find out which are the transformations that are changing your background. And what we find is something very similar as before. So we find that the transformations that change the background are ones that act on this Lie algebra with this upper triangular matrix. So now this guy is a constant transformation because it's just transforming this Lie algebra. Well, scrambling these generates of this Lie algebra amongst each other. But it's also of this upper triangular form. And then you also have the T action, which is of this off-diagonal form, and a combination of them. So we find some particular conditions for when this flux with three indices has to stay invariant. We get some conditions of this form. Here we have fluxes with lower and upper indices in various places. They are just different components of this flux with doubled indices. In particular, in this case, we get this zeta matrix. It's an antisymmetric matrix. You can multiply this with a deformation parameter, and so these guys capture deformations or integrable deformations, as I will explain. Now, from demanding invariance of the flux with one index, and again, demanding that you can extract some dilaton, so you get some usual supergravity, you get some additional conditions so that you remain in supergravity. And this particular equation that we have here, we classified this in our work with Falk by Lie algebra cohomologies of some particular subgroup of this doubled Lie algebra. Now there's also some freedoms that I didn't discuss. I will not go into more details, as I said, but please, during the rest of this week, you can ask me more about this. Okay, so now, as I said, these particular transformations, I said in the beginning, they are also canonical transformations at the level of the roll sheet, and so now I will tell you why that is. So we go back to the level of the roll sheet, so we go back to some roll sheet sigma model here, and we go to the Hamiltonian formulation, so we construct the canonical momenta, etc. What we can do is go to some sort of doubled space again, so it's very reminiscent as before. We can package these canonical momenta with the usual coordinates of the usual bosonic fields. And we dress that with some object E, which is exactly the same one as we had before. So it's some combination of the metric and the B field. And in that case, you see that canonical Poisson brackets between momenta and coordinates can be rewritten in terms of this guy psi A in this particular way, where we again see this flux appearing. So it's precisely the same combination in terms of the Vielbein that we had here. So it's exactly the same expression. And that is the only one that has some dynamical content. So this means that if you have a transformation that is changing your canonical data, so sending a psi A to psi A bar by changing your background, sending this generalized Vielbein to a new generalized Vielbein, but it would leave this flux with 3 indices invariant, then you would have a canonical transformation because you're preserving the form of the Poisson brackets. Now, I should emphasize that this is not a standard canonical transformation. It's not just reshuffling the canonical coordinates. It's a canonical transformation up to worldsheet boundary conditions, and this is very important. So the non-trivial information about this deformation will be captured in the worldsheet boundary conditions, as I will show you. Now, for homogeneous Yang-Baxter deformations, this happens when these two properties are again satisfied. And so as you see, we have less conditions here. So supergravity solution generating techniques are more strict. There we had also the invariance of the flux with 1 index. So here we see that we have more canonical transformations on the worldsheet than supergravity solution generating techniques. But every supergravity solution generating technique, all the ones that we consider, are also canonical transformations at the level of the worldsheet. Okay, so now let's see how this happens for homogeneous Yang-Baxter deformations. So I want to use this canonical transformation to really treat these two, the undeformed model and the deformed model at the same footing. So I want to compare the undeformed model with the deformed model, and to do that, I will use a different parameterization for the principal Cara model. So I have some group element G tilde, and then I have a parameterization G for the deformed model. Okay. Then it's very nice to see that everything that you want to know about your worldsheet sigma model, namely equations of motions and lax connections, if you have them, they can be very conveniently written in terms of currents. And so here for the principal Cara model and the homogeneous Yang-Baxter, we have some currents associated to a right-acting symmetry. So it's transforming this G tilde to G tilde times an object in the group. And a neutral current associated to that is just a Marot-Cartan form. And so in terms of the group elements, it takes this form. For homogeneous Yang-Baxter, we have the same symmetry, and the neutral current associated that is this guy, so it's a different expression. It involves the deformation parameter and this object R. But what is nice is that, so if you write down the equations of motions, they just look completely similar. So it's just a divergenceless property of these currents, and you can replace G tilde with A if you want. Also, the canonical variables, they are completely similar upon changing G tilde with A. And that is precisely what the canonical transformation is doing. So sending the canonical variables means that you're just replacing G tilde with A. And we know that it's a canonical transformation, that it satisfies the correct Poisson brackets if these two properties of homogeneous Yang-Baxter deformations are satisfied. Now, concerning integrability, this is nicely seen at the level of the currents again. So we have some conserved currents, and we know very well that if they are also flat, then we have classical integrability. And so flatness means that the current satisfies this condition, which for the PCM is just an identity. But upon changing G tilde with A, we find that this guy is also flat as it should. If these two conditions are satisfied, and also if you assume the equations of motion. So we get a lax connection for the PCM in terms of G tilde, which is just transformed to the homogeneous Yang-Baxter as this way. So just to say that we can have some on-shell equivalence between these two models when you're just equating these two currents with each other. So J tilde in terms of G tilde with A in terms of G. Now, of course, if we look at these expressions, we know that they are not identically the same. in terms of if you express them in terms of the group elements. So what you need to do is to introduce some twisting if you also want to relate the coordinates with each other. And so this twist that we introduce is the guy here. So G equals F, which is the twist field. Ah, my God. With G tilde. Yes, okay. And this implies some twisted boundary conditions, as I will show you. So we have this expression. If you assume for the deformed homogeneous Yang-Baxter, if you assume periodic boundary conditions, which is something normal to do because we already have a deformed space-time, but if you assume that then the group element of the undeformed model will satisfy some twisted boundary conditions. And they are given particularly here, so where W is the twist. So now, thinking back about the TST example, here we have some nonlinear relations for the twisted boundary conditions in terms of the coordinates, x tilde, because here we get just a relation in terms of the group element. And before for TST, it was just some linear relation that was given by a conserved charge. Yes?
Your twist W, does it depend on G tilde or it's universal?
So I will tell you that it is, you can construct it from G tilde, but it is constant. You can show that it's constant. So it is dictated by some conserved charges. But I will tell you that right now. So this particular observation was already known for quite some time. The problem with it was that people never use it really for practical purposes. And the reason is the following. So if you go to the homogeneous Yang-Baxter picture, where you write everything in terms of the group element of the deformed model, and you equate these currents, then you find some very simple relation between the twist field. I don't know why this. Should I do it like that? Okay, so you get this particular relation where between the twist field and the group elements, and you see that the variables are very nicely separated. You can just very quickly write down a solution for this equation, a solution for this twist field. And the solution is given by a path-ordered exponential of an integral of this object phi that was defined above. So it's very easy to write this solution, but you have a price to pay. So in particular, this expression is highly non-local because it involves a path-ordered exponential. So if you expand the exponential, you get some integrals of integrals of integrals and so on. And secondly, it's also quite an unnatural expression because it's written, the twist field is written in terms of the variables of the deformed model. So you're saying that you have some deformed theory with periodic boundary conditions that is on-shell equivalent to some undeformed theory with twisted boundary conditions, and a twist is given in terms of variables of the deformed model. So it's kind of unnatural. But it was easy to write down, but yeah, anyway, because of these two problems, it was not used for practical purposes. Now, what we did in the work with Louis was to rewrite this in terms of the PCM picture, so the variables G tilde. And then you get some relation that I write down here, which looks a bit more complicated because you get some relation between the twist field and G tilde, where the twist field and G tilde are not separated nicely. And I think that is the reason that it was not looked at in detail before. But what we did was to use properties that we know of homogeneous Yang-Baxter deformations, namely that they have some 2 co-cycle in them. Namely, if you invert the R operator, you call this W, then W is a 2 co-cycle due to this classical Yang-Baxter equation. And 2 co-cycles in the algebras have been studied for quite some time. They satisfy a lot of properties, and we use those properties to solve this equation in terms of the twist field. Now, let me just mention that we were not able to write down a closed expression for a general R matrix, but we are able to write down a closed expression once we specify the R matrix, because the R matrix is just acting on some finite dimensional algebra, and so you need to solve some finite number of equations, which can be done rather straightforwardly. So once this R operator is specified, you get a closed expression, which is local. There's no path ordering involved anywhere. And it's written in terms of the variables of the undeformed model. So it's a more natural thing to work with. Okay, so we get again this picture of the deformed spacetime with periodic boundary conditions and an undeformed spacetime with twisted boundary conditions, W. And of course, if we take eta to 0, the deformation parameter to 0, then we can just a truly undeformed picture where both the spacetime and the worldsheet boundary conditions are the usual ones. Okay, so now let me show you how you get some close expression for a particular case. So we look at here at Jordanian deformations. There are particular examples of homogeneous Yang-Baxter deformations, which you can write down once you have an SL2R subalgebra in your problem. So the SL2R subalgebra is given in terms of generators H and E plus and minus. They satisfy these commutation relations. And the algebra admits an antisymmetric solution to the classical Yang-Baxter equation. So here I write it down in a fancy way, but just the guy is just acting on the generators in this particular way. And then the expressions that we find can easily be inverted, and you can write a closed expression for the twist field, which I write down here. So it's given in terms of two objects, big Q and small q, which are written in terms of an object y, which in turn, so y in turn is found by the variables g tilde of the undeformed model. And in particular, so if you have a solution of your sigma model, you can just plug everything in and you will find what is the twist associated to your deformed model. Okay, and so this we have used in the work that appeared just today. To apply a Jordanian deformation to the ADS5 cross S5 superstring. So here I was, I think, yeah, I was a bit quick here. So here I should write down the supercoset sigma model. Basically, it just involves inserting some projectors, etc. But yeah, just to say, we have some sigma model where the Lie group G is, of course, the one of ADS5 cross S5. So it's PSU22/4. Okay. And this superalgebra admits an antisymmetric solution to the classical Yang-Baxter equation of Jordanian type. So it's of this form, where now E plus and H are just some particular combinations of the conformal generators of ADS5. Of the conformal algebra. So we have the dilatation operator and the boost, and then the canonical, the momenta operators. Okay, so this guy solves the classical Yang-Baxter equation and is antisymmetric, so you know that at the level of the worldsheet you preserve integrability. And it's also a supergravity solution generating technique, so in particular it's unimodular when you include this fermionic tail. So Q1 and Q2 are some particular supercharges of PSU224. If you don't have this fermionic tail, you still have a solution to the classical Yang-Baxter equation, and so you still have an integrable worldsheet. Okay, so now applying this deformation to the ADS5 superstring, ADS5 cross S5, we get a deformed metric that depends on the deformation parameter. In particular, the deformation is only acting non-trivially on the ADS5 part, so we just have here the round 5 sphere, and then we have the deformed ADS5 background. So I've written them down here in some unusual coordinates. They are global coordinates, which we specifically checked. And they are global coordinates for every value of the deformation parameter. So I want to emphasize this a little bit because, of course, we have global coordinates for undeformed ADS5 cross S5. But once you introduce a deformation, the causal structure of the spacetime may change. And so these original global coordinates are perhaps not good global coordinates anymore. And in fact, we see that a lot of isometries in these original global coordinates get destroyed, so they are not useful in this case. Here we find that the change of the deformation with what is called Schrödinger spacetimes is just this particular highlighted term. And Schrödinger spacetimes have been studied quite a lot in ADS-CFT, and also global coordinates are known for them. So what we did was to apply the transformation to global coordinates that was known for Schrödinger spacetimes, and then we checked if they also for this case are still geodesically complete. And so it is the case. And this was important for us because we wanted to have a global time coordinate T that in which we also have an isometry, so that we have a well-defined global energy associated to our problem, and that we will use to compute that we will use to in the spectral problem. Okay. Yes. So this is already in the global coordinates. The Poincare patch is obtained once you do the transformation back. So these x plus, small z rho, small theta, and x minus are the Poincare coordinates. Okay, so now I will go to the fact of trying to compute a spectral problem. And for that, we want to look at a particular solution of the equations of motion of your sigma model. And of course, it's very useful to mimic what you do in the uniform case. So you want to try to understand and study the most simple solution, namely a BMN type solution, which is a point-like string. So what we did was to have some point-like ansatz, and then the equations of motion can be very easily solved. And we find that, in particular, this time coordinate goes with the worldsheet time tau, with some rates a, where a is a constant. V also goes with tau with some constants involving the eta deformation parameter, and then some constant b. And then z just stays constant along tau. And of course, these satisfy periodic boundary conditions. Now what you can do is to translate to this twisted picture. We do this you have to be careful with some gauge ambiguities from PSU224, which we discuss in our paper, but eventually just end up with some solution written down here, which in particular depends on the sigma coordinates. So z tilde depends on the sigma coordinates in this way. So we get some extended string solution in the twisted model. And these satisfy periodic boundary twisted boundary conditions associated to the Jordanian twists, where the charges big Q and Q are given by this form. Okay. Now, I want to briefly take a moment to emphasize what is the advantage of using this twisted model rather than the deformed model for computing the spectral problem. So we have a flat Lax connection because we have an integrable model. And so that means that you can construct what is called a monodromy matrix, which is a disperse-ordered exponential. And this monodromy matrix has some constant eigenvalues. So the eigenvalues give you conserved charges, and so you get an infinite tower of charges when you expand around particular values of the spectral parameter Z. Now, in the undeformed periodic picture, so the truly undeformed picture, you have some unbroken symmetries. And if you look at asymptotics of this monodromy matrix, so you expand around some infinite value of the spectral parameter, you find some conserved charges that are associated to the usual Noether's charges. So they are particularly this QL. And they are particularly of local form, so the asymptotics of the monodromy matrix has some local conserved charges. In a deformed picture, the truly deformed picture where you have periodic boundary conditions, this gets completely scrambled. So basically, you look again at asymptotics of this monodromy matrix, and you find that if you expand around Z infinity, you find some very involved expressions which are highly non-local. Because of this path-ordered exponential, basically, even every term, even the first order term in the expansion, it will be a highly non-local expression. And this is something that you cannot use in your spectral problem. So because you really want your asymptotics of the monodromy matrix to have some local conserved charges. Now, in the undeformed twisted picture, things become nicer. So if you look at the asymptotics of the monodromy matrix, you will see that it involves some local expressions that involves also the twists. So it encodes information on the twists, as well as the next order is a local expression. It doesn't involve conserved charges, but it will involve conserved charges when you diagonalize the monodromy matrix, and in particular the asymptotics. And this brings you, so you can really look at the asymptotics, really try to understand the spectral problem because you have these local charges. So, and it brings you to what is called the classical spectral curve. which you find by diagonalizing this monodromy matrix. We introduce some quasi-momenta, pz, which are related to the eigenvalues of the monodromy matrix in this way. Now, in an 8x8 representation of PSU224, you will have 8 quasi-momenta. 4 will be related to the ADS space, so this is p hats. And then you have p tildes, 4 p tildes associated to the sphere. Now, as I said, if you expand around the asymptotics, you get conserved charges. In the truly undeformed case, in the untwisted case, you get the neuter charges in the Cartan of PSU224. And in the twisted case, you get eigenvalues of this twist, as well as the Cartan charges of the remaining symmetries of the twisted model. So in particular, because these twisted boundary conditions, they will reduce the number of symmetries, but here you will find that the Cartan charges of the residual symmetries appear in the asymptotics of the monodromy, of the eigenvalues of the monodromy. And for our Jordanian deformation, we find here in particular the charge related to the global energy, as well as a charge related to an isometry in angular coordinates, so it's some spin charge. And then we see also the charge Q, which is dictating the information about the twisted boundary conditions. Now, for our particular solution, you can compute these quasi-momenta, and you will see that they take this particular form. So I only wrote down the ADS5 quasi-momenta because they are the ones that non-trivially get deformed. And so what you should, for the classical spectral curve, we think of each of these quasi-momenta as some sheets, some Riemann surface, which for particular solutions share some cuts. So for our particular solution, we see that the p hat 1 and the p hat 4, they share a square root branch cut, and then p2 and p3, they also share this square root branch cut. Okay, good. So having these particular local charges in the asymptotics allows you to perform a well-known method put forward by Gromov and Vieira in 2007 to semi-classically quantize this spectral curve. And this method still applies to our case, so to the twisted model, up to some minor modifications, namely the modifications in the asymptotics of the quasi-momenta. And so the idea is to introduce excitations, quantum excitations on this cut in the form of microscopic cuts that we think of as quantum poles. So in the classical limit, so the full cut can be thought of as a condensation of poles. And when you put an excitation to it, this gives you some quantum correction to the charge. So we send P to P plus some quantum delta P, okay? Now, the interesting thing is that coming from the properties of the classical curve and also properties of PSU224, there are a lot of, there are very restraining properties also for the quantum excitations. I will not go into any details, but let me just tell you that they are restrictive enough to completely fix these quantum corrections. In particular, you can completely fix the poles where you can put the excitations, and you can completely fix their residues. And this allows you then, so you can fix them after doing just some algebra. It's rather straightforward, but it's quite some work. And this then allows you to compute the corrections to these local charges here. In particular, the correction to the energy. And you do that by modeling the fluctuations as some harmonic oscillators, as we know very well. And then we find a one-loop correction on top of the classical the classical energy. Oh, sorry, I didn't specify that. But for a particular solution, we have this global energy, which is just given by this A coefficient, which is determining the rapidity of this t coordinate. And so you can compute the one-loop correction on top of that. So that will depend on the classical energy A. So this coefficient A, and it will also depend on the deformation parameter as well as this parameter B that was a parameter that we had in our classical solution. Now, interestingly, we also see that the charge related to the twist that appears here does not receive any quantum correction. So it's sort of protected to on loop to quantum corrections. And this is quite interesting because it tells you that your twisted model is quite robust to quantum corrections. Now, let me also emphasize that we performed some particular checks. So if you turn off the deformation parameter, you won't have any correction to the energy, which is something that we know from BMN. And also from some explicit computations of the quadratic fluctuations of the Lagrangian, we see that some of our frequencies match with what you have here. Now, a result that I also want to highlight is that it seems that the spectrum is insensitive to whether or not you're looking at the unimodular or the non-unimodular twisted model, meaning that whether or not you are including this fermionic tail or you're not including the fermionic tail. And this is quite interesting because the non-unimodular case is not giving rise to a usual supergravity model. And so this we see for this particular solution in the twisted model. Okay, I think that brings me to my conclusions. So I looked at supergravity solution generating techniques. In particular, I looked at homogeneous Yang-Baxter deformations as supergravity solution generating techniques. And I showed you how in the formulation of double field theory, it's very efficient to see that they are that they have this feature. And this then allowed us to include a larger web of dualities and deformations with the same feature. And it would be very interesting to extend that setup to relax some of our assumptions, but also extend it in the world of exceptional field theory, heterotic DFT, etc. Also, their usage in holography, of course, will be very interesting for some lower dimensional examples to understand what is happening at the level of the CFT. Then I told you that at the same time, these transformations are also canonical transformations at the level of the world sheet, so they preserve integrability. And using that you have such a canonical transformation, a non-trivial canonical transformation, we could see these deformed homogeneous Yang-Baxter models as undeformed models with twisted boundary conditions. I told you how you get an explicit expression of these twisted boundary conditions. I think it would be very interesting to extend this to the larger web of dualities and deformations that we know. Let me emphasize that, of course, as I told you, we really need to use these properties of homogeneous Yang-Baxter deformations, namely those two co-cycles, to really get some explicit expressions. So it might not be straightforward for other type of deformations. But maybe there is some nicer way of reformulating the problem in some first order formulation. But that's, of course, very vague. Then we use this twisted picture to extend the integrable methods and apply them to our undeformed twisted models, and in particular get a first step to tackle the spectral problem of a Jordanian deformation of ADS5 cross S5. Then, of course, a very pressing question is what happens at the holographic dual, so at the deformed N=4 super Yang-Mills site. Do we have some spin chain with twisted boundary conditions, and can we match our computations with that? And so with that, I would like to conclude, and thank you.
So, thank you very much, Nabil, for the very nice talk. Do we have questions? All right, Linus?
So what does the dilaton look like for this deformation?
For the homogeneous Yang-Baxter deformation?
For the example you were discussing, this Jordanian deformation.
Oh, that's a good question.
In particular, is it finite everywhere, or does it blow up somewhere?
I think I cannot, yeah, I have not looked into that property. Yeah, maybe you.
Not off the top of my head, I'm sorry.
Yeah, it was not important for our analysis. As I said, like actually the unimodular and the non-unimodular case turned out to be the same. The whole analysis was done for the non-unimodular case, and then just right at the end we noticed that if you include this fermionic tail, it doesn't change your classical curve and the semi-classical quantization of it. So that's why I didn't really look at Dilaton. Yeah.
Okay. What about the metric? Is the metric regular, or is there a singularity somewhere?
So we looked at the geodesic completeness of this model. It doesn't have any singularity, so at Z is 0, you would think that there is some singularity, but it's more like the boundary of ADS.
Okay, thank you.
All right, further questions? Yeah.
I may have two questions. So first question is, this undeformed model with twisted boundary conditions could be interpreted as, probably it cannot be interpreted as a dynamics of closed string. No, it's something else, isn't it? So did you think about what could be interaction of such objects? Or
So like a string theory amplitude kind of
with
computation.
this monodromy, yes, because you know all stuff of Poisson-Lie duality, you know, works well only when you cut out the zero modes. Now you enter the zero modes into the game. On one side, it's pretty okay. It's your Jordanian deformed model. On the other side, you produce this monodromy. And from the point of view of integrability, all is okay. From point of view of interpretation, so at several people at all times of Poisson-Lie duality didn't know how to interpret it. It's neither open nor closed string theory, so what could be interaction of such object which develops such monodromy? And so did you think about that?
No, to be honest, no. I think it's a very, very interesting question, but for me, in my opinion, like this reformulation in terms of twisted boundary conditions, the power is really in integrability, where, as you say, it's completely fine.
It's completely fine. Yes.
Yeah, and where you can really use the non-integrable methods and just with some very minor stuff, very minor modifications, I can apply it to the twisted case.
And the second question is much related, and also because in all days we studied things from the point of view of Dreamfield double, which you didn't do. But did you think about how would be this twisted boundary condition from the strings in the Dreamfield double?
Yeah, so that's what I was alluding to in my outlook. So having some first order formulation for these twisted models,
Yes,
I think that would be amazing. Yeah, but I
think that it would be an interesting thing to work out.
I agree. Yeah, totally.
All right, further questions? Yeah, okay.
Well, it's probably a very simple question. Do you know how the Virasoro constraints transform under your transformation, under your twist?
Yeah, they are completely the same. So again, you can write down the Virasoro constraints in terms of these currents. Here, this is for the PCM, but it's just some particular projections of these currents in the case of the supercoset. For the undeformed case, is the projections of J tilde. And for the deformed case, it's the same projections of A. So again, you just can replace G tilde with A, and you're sure that also your Virasoro constraints are satisfied.
Right. So basically, that was the question. Yeah. When you talk only about sigma model, you don't talk about string theory. String theory also has Virasoro constraints, which has to be imposed, right?
Yes, yeah.
And when you do this transformation, it's not a canonical transformation. It's a transformation, well, you can call it locally canonical transformation, but since it changes the boundary conditions, it's not. You get two different models.
Mm-hmm.
And the question is whether this transformation can be done on the level of string theory, so that the Virasoro constraint would be still
Yeah, so regarding the Virasoro constraints, this is fine. Regarding GS corrections and stuff like that, this is a lot more difficult because we are in a Green-Schwarz formulation here and stuff like that. But regarding, as I said, Virasoro constraints are just mapped to each other under this sending G tilde to A. So if you satisfy them in the original case, you will satisfy them also in the twisted case.
Yes, so my question is, so you know, you've been imposing closed boundary conditions in all of this, and if you open the boundary conditions, you know that integrability might be broken. And the question is if you've tried to kind of consider which set of open boundary conditions would be integrable and then also be projected, be also integrable in the deformed situations.
Yeah, that's a very interesting thing that you can do. And it would give you some integrable debraying configurations and stuff like that. But here it's not, so really we want to look at a closed periodic model and compute things for that. But it's also something that is an interesting outlook direction. Yeah, I don't know if you can interpret that in some terms of twisted open boundary conditions. I have no idea how that would look like. Yeah,
probably that. But well, the other question is rather, so you studied the Jordanian in ADS5 courses 5, so maybe the next could be ADS4 cross CP, so ABJM kind of. So you think it's possible also? There's no kind of obstacle somehow?
Yeah, so as long as, thank you for the question because I think it's a nice point. So Jordanian deformations are particularly nice because they lead to diagonalizable twists in some particular class, up to some subtleties. But many of the other homogeneous Baxter deformations may lead to non-diagonalizable twists. So as long as you find some, I don't know, I never really looked in detail to ADS4, but as long as you have some SL2R subalgebra, which I imagine you have, you can apply such transformations. You have to, find an R matrix that satisfies these conditions of modularity in the classical Yang-Baxter equation. And then, I think the whole story rather straightforwardly goes through. You will, I imagine that you will find at the asymptotics of the monotomy matrix some local Cartan charges, and then you have to take care of like having these global coordinates and a global energy that is in this asymptotics of the monotomy matrix to really identify what is the quantum correction that you're computing. But, yeah.
Okay.
All right, then maybe I have a quick question as well, or two quick questions. So at some point you were mentioning you had a big Q and a small Q, and the small Q was 0, and so on. So it's sort of looking like your twist function only depends on one conserved charge in some way.
Yes.
But for these, like for the simpler example of these abelian ones, everything really always appears, like both of them appear on an equal footing, but here one of them disappears. Do you have like some interpretation to this? Like,
oh, that's a good point.
That's just for that specific solution.
Yes, but
So the small q was 0 was when specified the point-like solution. So we're just considering
okay.
particular string configuration and happens to 0.
well, I think maybe because you read the
Well,
paper.
wait, then I have one follow-up question. So.
Well, it's just a charge, so it's just a multiplication. It's
But so then I have a follow-up question. So these twists, I mean, algebraically you would imagine they are related to Drinfeld twists, and the Drinfeld twist for Jordanian deformation looks something like this, but not exactly. Is there is it clear that you could somehow, I don't know, pick a different gauge and get literally what you expect for a Jordanian twist, or is there something fundamental obstructing this? And if so, is there an interpretation to that?
I think I've never thought about this.
Okay, that's fine. And then one final question. This energy, that depended on two parameters, A and B. Is there a non-trivial choice of A and B where still the energy correction vanishes? Or is it generically non-zero for any A and B?
So okay, A something is an overall, will be an overall coefficient. And then the rest just depends on this combination eta over 2b squared, sorry, this thing. So if you're asking if I have maybe, so maybe let's call it beta, if this guy, if you have other values, yeah, that's a very good, yeah, I didn't try to look at this, but I imagine, yes, I mean, it's not just a linear expression, so,
Okay.
yeah.
All right, thanks. Any other final questions? No? Then let's, what? Was there one more question? Okay, Arkady, real quick.
So about this unimodular versus non-unimodular. So if you look at one-loop fluctuations, so the dilaton is not important. Fluxes are important. So maybe it's just for that particular classical solution, this difference is vanishing.
Yeah.
So it may be an accident of just choosing that particular solution that they match. Yeah.
We saw this in. So we analyze this in generality, not only for this particular solution, where you basically can factorize your twist, where the guy only, the non-trivial information is in this Q E plus. And this is under just one assumption. There's like two classes that we can look at, but yeah, basically for both of them we see that the fermionic contributions just don't enter in this at the classical level, and therefore also at the semi-classical level. But there may be some subtleties involved for some particular class. Now, also what I should mention is that this is we saw this for the twisted model. So in terms of the twist, there may be up to one loop, maybe some problems if you want to. So the equivalence with the twisted model and the deformed model is only classically. There may be, if you go to one loop, that there is some some problem if you want to equate them. So you should, there's some anomaly. Sorry, I couldn't think of the word. That if you want to try to equate them. Just to say that this insensitivity to the unimodularity case and the non-unimodularity case is for this twisted model. To really make a statement, you should also do a computation, some honest computation in the deformed model and compare that.
So I think we have.
Yeah, thank you.
So there's one final question and then we should stop.
With this technique, could you say something about beta functions of the sigma model? I mean, analysis, beta functions deformed or something like that?
The beta functions?
Yeah, right, of the sigma model.
Yeah, so in this, if you take this, no, I'm going in the wrong way. So if you include this fermionic tail, as I said, like you will still have a supergravity solution. The beta functions are still satisfied. If you don't include this fermionic tail, you will get some running of your deformation parameter.
Thank you.
Because you don't have a supergravity.
Okay, so let's thank Sibylle again for her talk. So right now it's lunch until 2:30. Please be back here by 2:30. Lunch is in there. You can eat outside, inside, whatever you want. Yes, thank you.